Namaste and warm welcome to this course on mathematical foundations for machine learning. In the past couple of weeks we have been discussing random variables. We have looked at a single random variable, moments and all those things, and then we started looking at pairs of random variables. We were trying to look at the joint behavior of the random variables. We looked at the joint probability density function, joint probability mass function, and then we looked at joint cumulative distribution function. And this idea of joint behavior comes from the idea of events, where we looked at A intersection to be the the probability of A intersection B is the probability of both event A and B happening together, and from there we took the idea of this joint probability mass functions and so on. Now we have come to a point where we are going to start with looking at the joint expected values. Remember, we had the idea of expected values of a random variable, and now what we are going to do is, the question we are going to ask is, can we do something like this, joint moments? Can we have joint expectations or expected values? Can we define joint moments? So those are the questions that we are going to answer in this particular lecture, and once this is done we will follow it up with conditional probability and conditional or conditioning of random variables and so on. Right now what we are going to do is we are going to look at the expected values. There are a few certain parameters which would describe the joint behavior of these random variables. Most importantly, you have the idea of correlation, covariance and so on. We are going to look at all that in this particular lecture. Okay. So let us go on, let us look at the joint expected values. So let us look at the expected values. Right, like how we had, recall, we had expected value of, let us say, g of x in case of a single random variable. We said that in case of discrete it is going to be g of x into p x of x, the probability mass function, let us say this x in the range of x, and we said this is going to be minus infinity to infinity. If it is continuous random variable we are going to take it as g of x f x of x dx. So this is what we had. Now what we are going to do is we want to look at the joint expected values. Is there something called as joint expected values? Now what do we mean by that, and how are we going to look at this? So this is what we are going to look at. So let us look at the joint moments, or okay, let us look at the expected value in case of the jointly distributed random variable. So so which means, suppose I say z is basically equal to, okay, z is equal to, let us say, g of x comma y, where x and y are some random variables, are random variables, right. Similar to what we had here, E of g of x is basically g of x into p x of x. I can do the same thing with discrete pair of random variable here. So I am going to look at E of z, which is nothing but expected value of, let us say, g of x comma y. We already know what is it in case of single random variable, so we are going to do the same business here. So I am going to write this as summation over, let us say, I, summation over j. I am going to write this as g of x I comma y j into p x comma y of x I comma y j, where p x y of x I comma y j is basically the joint probability mass function, right. So this is basically my joint PMF, right. So that is going to be my joint PMF. Now let us look at some specific cases, and then we will get back to something interesting. So, we have the following cases. So, what is that? I am going to look at, suppose z is equal to, let us say, g of x comma y, where x and y are random variables, which is given by the function is going to be just x plus y, right. That means what am I looking for? I am going to look at the joint expectation of this function, which is nothing but g of x comma y, which is nothing but e x comma y of x plus y. That means I am going to look at the expected value of the sum of the two random variables, right. I am going to look at this. So, how is this going to be done? This is nothing but sigma summation over I summation over j. I have x I plus y j into p x comma y of x I comma y j. This is what I have. But we know that okay, your this like whatever you have here x I plus y j into p x comma y of x I comma y j, you can see that you can distribute this operation. So, you have this is going to be I is I sigma j x I p x comma y of x I comma y j plus sigma over I sigma over j y j p x comma y of x I comma y j. This is what we have, right. Okay. Now, if you actually look at this, there is something interesting that happens. What is that? Let us take a look at this. If you say it is x I into p x y of x comma y, x I and y j, and you are going to do the summation over all y j, then what are we going to get? We are going to get the following. So, let us rewrite this. So, this is going to be this, I will write this as sigma over I x I sigma over j, because j is fixed over there. So, I am going to write this as, I mean j varies, I is fixed, x I. So, it is going to be p x comma y of x I comma y j plus, similarly I have this, I am going to write this as y j into sigma over I. So, this is going to be over j, I am going to have p x comma y of x I comma y j, right. Now, you can notice something very interesting. What is this? This is going to be fixing x I, and then we are going to sum over all j. That means this is going to give me my marginal PMF. So, this is nothing but p y of y. Is this clear? So, this is this is going to be p, okay, sorry, this is going to be p x, this is going to be p x, because you are going to sum over y. So, sum over all j's. So, this is going to be p x of x I, and if you look at this, this is going to be fixed y j, and I am going to look at summing over all x i's. So, this is going to give me p y of y j, which means, which implies what am I going to get? I am going to get summation over all I x I. We saw that this p x y of x I comma y j, when you sum over j, is going to become p x of x j x I, then plus sigma j over j, I am going to have y j p y of y j. This is what I am going to have. And what is that? That is interesting. This is of the form summation x into p of x, which is nothing but expected value of x, and this is going to be summation y into p y of y, which is going to be expected value of y. So, this is going to be expected value of x plus expected value of y. So, what do we mean? What do we infer from here? We say that the expected value of sum of random variables is nothing but the sum of expected values, right. So, we are going to write this expected value of sum of random variables, value of a sum of random variables you can do the same thing for continuous distribution also, continuous random variables too. So, sum of random variables is the sum of expected values, is the sum of expected values of the random variables. Right. That is a very important understanding. The extension of this would basically be this. What we are going to say is we are going to say the expected value of, let us say, a times x plus b times y is nothing but a times expected value of x plus b times expected value of y, right. Therefore, this is what we had seen even before. We are going to say that the expected value or the expectation operator or expected value or the expectation of x or the expectation is a linear operation. It is a linear operation. Now, the next thing that we want to look at is we have looked at sum of random variables. What we are going to do is we are going to look at the expected value of the product of the random variables. So, what are we going to do? We are going to look at expected value of g of x comma y, where g of x comma y is nothing but x y, the product of the two random variables. So, I am going to look at E of x y. E of x y is nothing but summation over I, summation over j. I am going to have x I into y j into the joint probability mass function, right, into the joint probability mass function. I will do the continuous counterpart in some time from now. I will just do it with the discrete. I will get back to the continuous in a few minutes from now. Okay. Now, this is interesting. Expected value of x y is equal to x I into y j, probability, the joint probability mass function of x I comma y j. Now, in this case there is a name for this E of x y, there is a name for this. The name that we give for this is basically, this is called the correlation. E of x y is called correlation. This is a very important metric that we want to look at, but what we will do is we will pay more attention to the sign of the value that we get. Okay, we will emphasize on the sign of the number that we get. Okay, so this is basically this. Now, a very important thing that we want to see, we are looking at the joint expectation. That means where we are looking at expected value of x y. Now, when we say expected value of x y, that means product of the two numbers, the two random variables. In the case of sum, we said that expected value of the sum of random variables is equal to the sum of expected random variables. Now, there is a small curiosity in us which is going to make us ask this question: can we have expected value of x y to be equal to expected value of x into x plus expected value of y? That means, is the expected value of the product, can the expected value of the product be equal to the product of the expected values? That is a pretty interesting question, because we just saw that the expected value of the sum is equal to the sum of expected values, and we said that expectation is basically a linear operation. Now, the question that we ask is, can there be occasions or can there be scenarios where expected value of x y is equal to expected value of into x into expected value of y? That means the expected value of the product is equal to the product of the expected values. The answer is of course yes. When x and y are independent random variables, expected value of x y will be equal to expected value of x into expected value of y. Now we must also understand, is the converse true? Suppose if E of x y is equal to E of x into E of y, can we call them independent? No, we have to exercise caution there. Whenever the random variables are independent, expected value of x y will be equal to expected value of x into expected value of y, and if this happens, can we call them independent? No, you cannot call them independent. We will come to that a bit later, but just remember this. So let us write this: if x and y are independent random variables, then when do we call them to be independent random variables? The joint probability mass function is equal to the product of marginal probability mass functions for all values of xi and yj. Only then you call them to be independent. Suppose if they are independent, then what we say is okay fine, something interesting happens here. So then E of xy is nothing but sigma I summation over j. I have xi into yj into px comma y of xi into xi comma yj. But because they are independent, we know that the joint probability mass function is equal to the product of the probability mass function. So which means now I am going to write this as summation over I xi px of xi summation over j yj py of yj, right. That is because independent random variables implies the joint probability mass function is equal to the product of probability mass function. So this is nothing but expected value of x into expected value of y. Is this clear? So what are we going to say? We are going to say that if the random variables are independent, then we are going to do this. So let us write this. So if x and y are independent, if x and y are independent, then expected value of let us say g of x into h of y is equal to expected value of g of x into expected value of h of y. Is this clear? So this is what is there, but reverse, no, let us not look at the converse of this right now, right, saying that if these two are the same, then can the variables independent. We will not get to that right now, we will look at something else. Okay. The third thing that we want to look at is basically the following. I want to look at the variance of sum of random variables. What am I looking for? I am looking at let us say z is equal to x plus y, where x and y are two random variables. Now what I want to look at is I want to look at variance of z. So I ask, what is variance of z? We already know how to compute the variance of a random variable. Variance of z is nothing but expected value of z square minus expected value of z the whole square. This is something which we know, right. Now let us write this is same as expected value of x plus y the whole square minus expected value of x plus y the whole square. This is what I have. So, let us do a term by term expansion and see what happens. I am going to have, first I am going to take this as term T1 and I am going to take this as term T2. So, I am going to expand T1 right now. T1 is nothing but expected value of x plus y the whole squared, which is nothing but expected value of x squared plus expected value of y squared plus, now what we have is 2 times expected value of x y. I have applied the linearity property of the expected value operator. So, it is going to be expected value of x squared plus y squared plus 2 x y. I have applied the property linearity property. So, the expected value of sum is nothing but sum of expected value. So, we get this. Now, I am going to look at T2 and see what happens with T2. T2 is nothing but e of x plus e of y, e of x plus y the whole squared, which is nothing but the expected value of sum the whole squared, which is nothing but expected value of x plus expected value of y the whole square, which is nothing but e of x the whole square, that means the expected value of x whole square plus expected value of y the whole square plus 2 times the product of expected values e of x into e of y. Now, what I am going to do is I am going to do T1 minus T2, because that is what we had. T1 minus T2 is nothing but e of z square minus e of z the whole square. This is what we have. So, this is nothing but expected value of x square plus expected value of y square plus 2 times expected value of x y, and I am going to do the subtraction T2, which is nothing but expected minus expected value of x the whole square minus expected value of y the whole square minus 2 times expected value of x expected value of y. Now, if you look at this term by term, I have actually written it so that it is easy to understand. So, now look at this. This is nothing but expected value of x squared minus expected value of x the whole square, which is nothing but variance of x. Then if you look at this, what is that one? If you look at this, e of y squared minus e of y the whole square, that is going to give me variance of y. Now, there is some new term that comes up, which is nothing but plus 2 times e of x y minus e of x into e of y. Right. There is another new term that comes into picture here. Now, what is that new term? What is that new term? This new term that we have here is what we are going to call as the covariance of x comma y. We are going to call that as the covariance of x comma y, like how you had the variance of x, variance of y. I am going to call this as the covariance of x comma y. So, let us write this. So, covariance of x comma y is nothing but the correlation, that means expected value of x y minus the product of the expected values. Right. I mean it is also easy to see, there is also easy what would you call way to look at this. Recall that we did something called as the moments about the origin, then we said the moments about the mean in case of single random variable. That is exactly what we are looking at here. I am going to define my joint moments as the following. So, let me define, I will then come back to this covariance case. So, I am going to define the joint moments of x y. I am going to define this, again I am going to define it in two ways, one is joint moments about the origin and the other one is joint moments about the mean. So, I am going to look at that. So, I am going to look at the joint moment about the origin, which I am going to write this as expected value of x power I y power j, which is in the case of discrete random variable given by, let us say x I. Okay, let me put this as let me just change this is going to be m n. So, I am going to write this as x I into y j, but it says x power m y power n. So, I will write this as x power x I power m y I power n. I am going to write this as p x comma y of x I comma y j. This is the joint moment about the origin. So, suppose if I put m is equal to 1, n is equal to 0, I end up getting the expected value of x. If I put m is equal to 0, n is equal to 1, it is easy to observe I am going to get expected value of y. The 1/1th central moment, I mean 1/1 moment about the origin, which is nothing but expected value of x y, that is the correlation. This is what we call as correlation, right. This is what we call as correlation. And the most important thing is, if E of x y is equal to 0, we say the random variables x and y are orthogonal, x and y are orthogonal. That is the most important idea. We say x and y are orthogonal, we do not give any other thing. If you say the correlation is 0, we say that x and y are orthogonal to each other, orthogonal random variables. Now, what I am going to do is I am going to look at now the joint moments about the mean, joint moments about the mean. So, what I am going to do, I am going to look at this as expected value of x minus E of x, right. Again I will put this as m, and y minus E of y power n. So, what is this? This is the joint m nth moment, central moment or moment about the mean. Okay. Now, if I put m is equal to 0, n is equal to 1, it is going to be okay. Let us see what happens. Let us say m is equal to 1, n is equal to 0, implies I am going to get expected value of x minus E of x. What is this expected value of x minus E of x? This is nothing but expected value of x minus expected value of x. But expected value of x is a constant. So, expected value of x is going to be expected value of x itself. So, this is going to be 0, this is equal to E of x itself. So, the 1/0th central moment is going to be 0, 0/1th central moment is also going to be 0, because you are going to get expected value of y minus E of y the whole power n. So, that is also going to be 0. I mean that is no surprise, because it says you are trying to find out the average of set of numbers. Suppose I have a set of numbers, I have a data which is captured in terms of the variable y, I compute the average for y and then I subtract the average of y from each of those data points that I have, and then I take the average. I think we took an example like that. We said okay, I am going to have numbers 1 2 3, the average of this 1 2 3 is basically 2. Now, what I do I subtract 2 from each of these numbers. So, I am going to get minus 1 0 and 1. Now, you take the average of this mean subtracted data, the resulting average will be 0. That is exactly what we see here. And we will also say n is equal to m is equal to 0, n is equal to 1, that moment is also 0. So, what is interesting, we want to look at this expected value of x minus e of x power 1, the 1/1th joint central moment we are going to look at into y minus e of y, right. This is the 1/1th joint central moment now. What is this? I am going to have let's try to expand and see what happens here. So, I have expected value of x in minus e of x into y minus e of y. So, this is nothing but okay, let me rewrite this. This is going to be x minus e of x into y minus e of y. Let me expand this bracket, multiply terms and then see what happens. I get x y minus x e of y minus y e of x plus e of x e of y, right. What we have, this is nothing but again expected value of sum is equal to sum of expected value. So, I will write this as expected value of x y minus this is e of y, e of x into e of y. So, e of y is a constant. So, that becomes a scalar for this. So, I am going to get e of x into e of y. Similarly, for this term e of x becomes a scalar because that is a constant, and then I am going to get e of y. So, I am going to get e of x into e of y plus expected value of e of x into e of y, that is basically a constant. So, I am going to write this as expected value of x, expected value of y itself. So, one of these terms get knocked off with this. So, what I have is expected value of x y minus e of x into e of y, and what was that? This was basically the covariance that we saw some time back, covariance of x comma y. So, the covariance of x comma y is nothing but the 1/1th joint central moment. This is called the covariance of x comma y. Is that okay? Great. Now, there is a small problem here. Let us see, let us try to understand this covariance a bit. Let us try to understand this a bit and then we will come back to discussing this a bit more in length. So, we will look at this. Again I want to see the idea of x and y being independent, then what happens. So, we are going to do this expected value of let me write covariance of x y. Covariance of x comma y is nothing but expected value of x y minus e of x into e of y, right, minus e of x into e of y. Okay. So, what are we going to do here? Suppose if covariance, there can be situations where the covariance of x comma y is equal to 0, it can become 0. What does that mean? That means this entire thing can become 0, e of x y is 0, then e of x is 0, e of y is 0, or e of x is 0 and e of y is not 0, whatever it is. There is going to be one of these two product terms to be 0 or both of them to be 0, and this one is 0. Then what happens? Covariance becomes 0, or it can be something like e of x comma e of x y is to be equal to e of x into e of y, which means the covariance can be 0. So, now what are we going to do? We are going to look at this. We are going to say, look, if the covariance of x comma y is 0, if covariance of x comma y is 0, we say that x and y are uncorrelated. We are going to say they are uncorrelated okay, they are uncorrelated. I will come to this again, interesting insight, we will get this, we will get it here, we will get back to that. Okay. Now, remember when we did the the when we look at the joint behavior, we said that look, the random variables can be independent of each other, these two random variables x and y can be independent of each other, right. Now what are we going to do? We are going to look at this. Suppose if x and y are independent, then we say that then we see, remember in couple of slides back we saw this, what was that? We said that if x and y are independent, then E of x y is equal to E of x into E of y. So if they are independent, then what we do? We are going to say that we see that covariance of x comma y is 0. Okay. So we are going to make one interesting statement here. What is the statement? We are going to say, look, if they are independent, they are uncorrelated. However, if they are uncorrelated, they need not be independent. So we are going to say this. Note, if x and y are independent random variables, they are uncorrelated. However, uncorrelated random variables does not imply independence. Right, it does not imply independence. Now let us get to this. You remember we were actually trying to derive the variance of the sum of random variables. We said variance of z is equal to variance of x plus y. Suppose if z were to be equal to x plus y, we were actually deriving the sum variance of the sum, which was equal to variance of x plus variance of y plus 2 times covariance of x y, that is what we had, right. Now suppose, let us do this, suppose x and y are independent random variables, then variance of z is equal to variance of x plus variance of y, right. That means what are we going to say? We are going to say that if z is sum of independent random variables, then the variance of z is nothing but the sum of variances. I will write this notation, variance is given by sigma, the variance is given by sigma z square, where sigma z is basically the standard deviation of z. This is equal to sigma x squared plus sigma y squared. This is what we have. Have we seen this somewhere before? Of course we have seen it. When we looked at binomial random variable, where the binomial was considered to be n independent and identically distributed Bernoulli trials, we said that the variance of binomial distribution is nothing but the sum of variances of your individual Bernoulli distribution. Suppose you have sum of you look for n independent binomial Bernoulli trials, we said that the variance of n independent Bernoulli trials is nothing but the sum of n independent variances, that the sum of variances, that is what we saw there. So it is not something new, we have already seen this, but we are formalizing it right now, right. So, we see that sigma x squared is equal means z squared is equal to sigma x squared plus sigma y square. Now, does this formula ring a bell somewhere? Does this formula ring a bell somewhere? Of course, it looks like something which is very familiar to us. What is that? A squared is equal to b squared plus c squared, and what is that? Pythagoras theorem. So, this is basically the Pythagoras theorem in statistics. The variance of sum of independent random variables is nothing but the sum of independent, the sum of variances is basically the Pythagoras theorem in stats. The statistical version of Pythagoras theorem, or the probabilistic version of the Pythagoras theorem, it says the variance of sum of independent random variables is nothing but the sum of variances. Okay, that is great. Now, there is still one more thing that we want to look at. What is that? Uncorrelated random variables does not imply independence. Now, how are we going to look at this? Let us look at what happens here. It says need not be independent, therefore, there could be cases where uncorrelated can be independent, there could be cases where uncorrelated need not imply independent. So, we are going to look at both the cases, right. So, we are going to look at a couple of examples here. We are going to look at a couple of examples, but before we get into the examples, let us re-emphasize on what we want to do. We want to prove, or we want to look at independence imply independence imply zero covariance. However, zero covariance does not imply, need not imply, we will probably have a clause there, we will say does not imply independence. So, what we will do is we will stop with this, the idea of independence and zero covariance and stuff. We will stop with this. When we come back for the next class, let us see what this actually means. Zero covariance does not imply independence. What does that mean? Can we look at an example where the covariance is 0, however, the random variables are not independent. So, what is the basic idea of independence? Independence means occurrence of one event does not give any new information about the occurrence or non-occurrence of the other. That means you take events A and B, given that event B has occurred, I do not even know if event A has occurred or not. It does not give me any update, it does not give me any new information, I cannot update it, right. The same is what is happening here. So, what it says is, look, I have zero covariance, that means I know that these two guys are they have a zero covariance, that is what it means, but can we say that, look, they are not independent? That means despite knowing that it has zero covariance, can we come and say that, okay, because they have zero covariance, okay, there is no way that they are independent. That means knowing x, does it give no information about y? Knowing y, does it give no information about x? And that is a question that we are going to answer in the next lecture. Namaste.